Before we get started, I just wanted to mention that I sometimes have called epsilon E and kappa K. Just a mistake. I'm sure you can tell from the typesetted version which one is which. Now we're going to talk about how to beef up a parallel plate capacitor. This is very simple stuff, but I want you to be able to derive any and all of this material. I suggest you take good notes and try to understand all the steps. So one more time, consider a parallel plate capacitor, and it has metal plates with vacuum first between the plates. Let's suppose we take this battery and we connect it to the plates like this, and therefore charge will flow out onto the plates. This is always the negative, this is always the plus part of the battery. So we get negative charge density here, and we get positive charge density here, and we call this plus sigma F and minus sigma F because this is free charge. If we break this circuit after we've charged the capacitor up, this charge stays there. It doesn't change. No matter what we do, take a wire from here to here, which we're not going to do, this surface charge density, the free charge density, will stay the same. You know how to find the E field between the plates, but let's just do it again. You take a pillbox of area A. This side's parallel to the E field because of the symmetry. We know the E field is normal to the surface. The area here A and the area here A will be what we need for the surface integral. Because this is either in the metal, or if this is very thin, it's infinite, the E field here is 0. So the net result is that we can bring the E field out of the surface integral, and E times A is equal to sigma F times A divided by epsilon naught, and that gives us the E field. This is the free E field that we're talking about. We can either call it E1 or E free, doesn't matter. Because this charge density will not change, E free will also not change. And what I mean by change, not change with what, we're going to slide in a dielectric between the plates. So here we go. We slide in the dielectric. We're going to maintain a small spacing here between the plates because we'd like to talk about the field here versus the field here. So now we do the same thing. Gauss's law confirms up here, where we're in vacuum or in air, the E field and the E free is the same. Now this E field exists all the way from here to here, regardless of whether or not there's a dielectric. So the free E field that comes from the free charge can penetrate and exist in this region here. Likewise, down here, where we have negative charge density, because the normal vector changes sign, we get the same E free down here. So if we use the negative charge, we'll get the same thing. And if you wanted to say this, the E field is really due to the combination of these two charges, but we only use one charge density in a pillbox to find that E free. Saying it again, because the magnitude of sigma F on the bottom is equal in magnitude to the surface density on the top, the E emanating from the bottom plate is equal in magnitude and direction to E free. Now the E free generates a polarization vector. That's the vector P due to all of the induced dipoles in the dielectric. It also produces bound charges plus and minus sigma B, the bound surface charge density on the surface of the dielectric. That's by polarization of the dielectric. These do not change E free. That stays there. There's no bulk bound charge produced because of the symmetry. There's no change in the P vector as we move around inside of this dielectric. The bound surface charge does create an induced electric field. So what we're going to be doing then is adding to the E free the E field due to the bound charge. So that's being stated here. The bound surface charge creates an induced electric field E sub B, where B is bound, which is in the opposite direction of E free. We can determine E sub B in terms of this surface charge density by using this Gaussian surface. So here's the bound charge, and we put our Gaussian surface, the pillbox, just outside and then inside the dielectric. go through the same arguments about the symmetry and the area and so on, we come up to the following. E sub b is equal to sigma b over epsilon naught. We could have used the negative charge density up here to come to the same conclusion. We can argue later why this is true, but for right now we'll just assume that the E sub b is less than E sub free. These are magnitudes. This is generally the case. I've repeated the equations for the magnitude of the free E field and the bound E field due to the surface bound charge. We add these together to find the total E field inside the dielectric, and that's equal to the sum of these. You realize that this is pointing in the opposite direction of E free. So if we look at magnitudes, then the magnitude of E total will be E free minus E sub b, where these are the magnitudes of the fields. For a linear dielectric, we showed that the E total is equal to the free E divided by kappa. Let's state that again. This is the E field that's inducing the polarization coming from the free charge. This is the total E field inside the dielectric. And what you see here is you get the shielding effect because of the kappa being greater than 1, so this quantity here is less than E free. It's in the same direction as E free, and in our case that would be the minus Z direction. So let's go back and look. You can see here that E free is going in the negative Z direction, E sub b is going in the positive, the net E is going in the negative Z direction. If we now take this E total, just remind you, it only refers to inside the dielectric. Given these magnitudes, where we have this set of equations here, so E total is this over this, equals E free minus E sub b, so we're back to magnitudes. Let's solve this for E sub b. So what we have here is E sub b equals E free minus E free over kappa. This is E total. Factoring out the E free, we get this times 1 minus 1 over kappa, E free. Now we can do the same thing with charge density, because we know that E sub b is equal to this quantity here. That came from Gauss's law. Again, from Gauss's law we got the free E field equaling this. If we take E sub b and set it equal to the E free, we're basically doing this equation again, or this one here. We can put in the E free equaling sigma free over epsilon naught. That's right here. And we have the factor 1 minus 1 over k, and of course the epsilon naught. So from that, we can just multiply by epsilon naught. We can get the bound charge density in terms of the free charge density. So here it is right here. And again, notice that this is larger than this. All of these are magnitudes because they're scalars. If you want to, you can get the sign of these things depending on what plate you're at, the top or the bottom. So if you want them, you just simply have to figure out which is which according to the diagram. So suppose we have a charged capacitor initially with no dielectric, with a charge density sigma f, the free charge, and then we insert a dielectric. And what we're going to find is the potential changes, and we'll calculate how much. So we have an isolated capacitor, initially no dielectric, and free charge, plus or minus sigma f. And we take the total gap to be almost completely filled with a dielectric when we insert it. The potential across the capacitor before we insert the dielectric we'll call V old. And this is equal to E free times D. And the way we got that was by integration of the E field across the gap. Here's E free integrated from 0 to D to give us the V old. Okay, so now we shove in the dielectric, and we're going to do it in such a way that the free charge is untouched, it does not change. And we still have E free equaling sigma f over epsilon naught. The E field in the gap is the E total. That's the E field inside the dielectric. So to get the new potential, we integrate E total dx from 0 to D. And so because of the fact that this is a constant, we end up with E total times D. Well, E total is represented by E free divided by kappa. This new potential is equal to this quantity times D. But if you go up here, you'll notice that the old potential is just E free times D, so that's E free times D, so we can replace that with V old over kappa. So the voltage across the capacitor dropped by a factor of 1 over kappa. The larger the kappa, the bigger change in the potential, and the lower value of V new compared to V old. We can derive this expression another way using Gauss's law. I'm going to do that by taking another pillbox, and I show it here as number 3, where the upper side is again in zero field, but now the lower side contains both the free charge density and the bound charge density on this particular surface. We can still use Gauss's law. Remember, we could use Gauss's law for the bound charge, we could use it for the free charge, or we can put the two together. So doing that, if you look at the expression for Gauss's law, we know the general equation is equal to Q total enclosed divided by epsilon 0. Now Q total is equal to the free charge enclosed plus the bound charge enclosed divided by epsilon 0. So going back to charge densities, we have sigma free and then minus sigma b because it's minus times A will give us the charge enclosed in the box. This thing here is A, pillbox, like that. So this is A, and then divided by epsilon 0. But we've already determined that sigma b is related to sigma free, like this. So we can eliminate sigma b by taking sigma free, that's this one right here, minus sigma b, which is this quantity right here, so I put it right here, times A divided by epsilon naught. And then crank and grind, get rid of things, and what you have, 1 over k sigma free times A divided by epsilon naught. That is the right hand side. The left hand side, we go back and do our tricks of normal E field. E is constant on the surface S, and so we're left with E total times A is equal to the right hand side. If we simplify that over there, you can see that it's sigma free times A divided by kappa epsilon naught. I'll cancel the A's, and we get E total in terms of the free charge density. But then remember that sigma free over epsilon naught is E free right here. If we divide by kappa and then put it into vector form, then the vector corresponding to the internal E field inside the dielectric is equal to minus sigma free kappa epsilon naught times Z hat. E total is in the same direction as E free. Simplifying by adding the equation for E free in terms of sigma, we end up with E free divided by kappa. And so we've given an equation that we derived earlier in terms of sigma free or E free and kappa. Here's E total in terms of sigma free, and here it is in terms of E free. In both cases you have a kappa down below. Now we want to consider D and the polarization. Let's start with D. Remember that D only depends on the free charge. We can use Gaussian surfaces similar to what we did before. Here we have a Gaussian surface that only includes the free charge density on the plate. We calculate D. This Gauss's surface dips into the dielectric and has the bound charge and the free charge. D only depends on the free charge. So it's like this wasn't even here. If we go down here into the gap, where we're in the gap here, the only charge that's enclosed is this negative free charge, and because of the change in the normal direction corresponding to this surface, we end up with D headed down in this direction, as we've seen here and here. All these D's are the same. They're the same magnitude and direction. To get that, you go through Gauss's law again. This is only the free charge. If you say between the plates anywhere, the D will be equal to minus sigma free times z hat. See, there's no epsilon naught here. That's equal to epsilon naught E free. And so we have d in terms of sigma free or E sub free. Between the plates, d remains the same inside or outside the dielectric. And I've just repeated that up here. So now let's look at P. We're only concerned about inside the dielectric. P outside, so up in the gaps here and basically up here, P is equal to 0. But as soon as you get in the dielectric, you've induced some dipoles, and so P is non-zero. We're going to assume a linear dielectric, and remember what that means. It means that P is proportional to the E inside, and so that's what I call E total. And the proportional constant is epsilon 0 chi sub E. This is the permittivity of free space, and this is the electrical susceptibility of the dielectric. Remember that E total is equal to this quantity in the negative z direction. So using our equation for E free, which is sigma free over epsilon naught, we come back to that equation where you have E free over kappa and times the minus z. So this is just a reminder of what we've done already. So what we're going to do is we're going to put E total into the polarization equation, and so we stick that in. That's equal to epsilon 0 chi sub E, E free divided by kappa. But then remember what K is. It's equal in magnitude to epsilon r. It's equal to 1 plus the susceptibility chi sub E. So we can solve for chi sub E, and it's equal to kappa minus 1. This comes up so often you better try to memorize that. This is the way we get kappa and epsilon r. We set it equal to 1 plus chi sub E. We want to get this in terms of the k minus 1 factor. This is substituting for the chi sub E, and so P then is equal to epsilon 0, kappa minus 1, chi sub E, sigma free, kappa over epsilon 0 minus z. Remember that all of these are going to end up positive because kappa is greater than 1. P is in the minus z direction, which is in the same direction as E free and D. We replace sigma free over epsilon naught with E free. Rewriting this then, we have P equaling this function here in the minus z direction. So we have it in terms of the free charge density, or it's equal to this in terms of the E free value. That gives us P in terms of sigma free, E sub free. By the way, we did the same thing for E total. We're doing this as a function of these two values. Taking into account that K is greater than 1, we see that P points in the same direction as E free. Let's look at capacitance now. This is really one of the major applications of dielectrics. So we have a dielectric that we're going to slide into this system. We've charged it up and taken the battery off. We have these fixed charge densities. So we shove the dielectric in. We're interested in what is the capacitance. The new voltage, which we talked about earlier, was equal to these quantities here. So the new voltage drops because the kappa is greater than 1. This is the old voltage. So we have it in terms of E and sigma. The capacitance with the dielectric is defined as it would be in general, the free charge on the plates divided by the new voltage. Remember that when we charge a capacitance, the battery gives the system Q free. So that's why we have Q free here. However, the voltage across the plates is equal to V nu. So that's going to change the capacitance for the unfilled capacitance. Putting in our various terms here, Q free is sigma free times A. V sub nu is given by this, so that came from up here. Simplify this and you get kappa epsilon 0 A over D. That's the capacitance of the unfilled capacitor. You could call it no dielectric. So kappa times the unfilled capacitance is equal to the capacitance with the dielectric. If we go through the different arrangements, if you look at kappa epsilon 0, that's this one right up here, that's equal to E0 E sub r because these two are equal. And so that's equal to the permittivity of the dielectric. So if you stick that in, the capacitance with the dielectric is equal to the epsilon, the permittivity of the dielectric, times A over D. So if you compare these, then we can see, it's easier to see right here actually. If this is greater than 1, the capacitance with the dielectric is greater than with no dielectric. And obviously the bigger the kappa, the bigger this inequality becomes. So this is what we mean by beefing up the capacitance by using a dielectric. This is how the voltage depends on all the parameters that we're talking about. How does the voltage interact with these various fields and so on? So what we're going to do is consider the old voltage, which is what we apply. That will be the battery voltage. And we're going to apply it, for example, to the C with the dielectric. Now, because the C with the dielectric is greater than C no dielectric, then we're going to get a larger Q when we have the dielectric, and it'll be the free charge larger than the Q that we had before with no dielectric, considering only the free charge. Think about this a little bit. Before, you charged the unfilled capacitor and you got a Q given by this right here. When you have the dielectric in order to get the same voltage, you have to give the capacitor more charge. The relationship with the capacitance with the dielectric will be the free charge divided by V. And think of this as the battery voltage. So go through your capacitance equation that we had with the dielectric, and it's equal to this quantity right here. This would be your epsilon if you wish to put it in. We also know that the sigma with the dielectric is going to be equal to the Q with the dielectric free charge divided by A. We're going to combine these two equations. What we get then is the sigma with the dielectric, the free charge sigma, is equal to this quantity here. So epsilon r, epsilon 0, V over D. This gives the free charge density as a function of the applied voltage V. And that's what we're trying to do. We're trying to get the voltage dependence of all these parameters, fields. Given that we have the free charge, we can start looking at the D field, the E field, and the P. And so let's do that in terms of voltage. We say that D everywhere, remember, only depended on the free charge density. It's going to be in the minus Z direction. Throw that away. And that's equal to minus epsilon r, epsilon 0, V over D times Z. This is what we got before for D. Now this time it's the voltage that we apply with the battery. E with the dielectric free is another field that we can get. This will be a free E field, and that will be larger because we have a larger sigma free. So if you take the sigma free divided by epsilon 0, and this is with the dielectric, this is E with the dielectric, then what you find is that that is increased from what we would have gotten without the dielectric, which is V over D. So then we have the total field. This is the E field inside the dielectric, and let's see how that depends on the battery voltage. Well, you go back to what that was. That was 1 over kappa, what I show here, or 1 over epsilon r, which I show here. This is E with the dielectric free, which we've just calculated. Putting that in, epsilon r drops out, and so you're with minus V over D Z. P was the equation for P in terms of the charge density was equal to this. This is the free charge density on the metal plates. It does not include any bound charge. Putting that in, we have sigma free with the dielectric. Keeping track of all these epsilons, we have this factor here for this one. We're putting in sigma free, which is equal to these constants and voltages and distances and so on. Simplify that, we have minus times a term that is greater than 0 times epsilon 0 V over D times the z hat. We can get this in terms of chi by using this relationship. So putting P in, this would be equal to epsilon 0 chi sub E V over D z hat. Let me just clarify. This comes about by taking this P and putting in epsilon r equal to 1 plus chi sub E. What that equals is E0 chi sub E times E with the dielectric total. And that is right here. This is E with the dielectric total, which is up here, right here, in terms of magnitudes. That's what we would expect, but remember that P is proportional to the E field inside the dielectric, and that's what this is here. In case of keeping the battery on, we get a bigger polarization than we would if we didn't keep the battery on.